All right, so we're going to talk a little bit here about simple harmonic motion. The very first thing up at the top there gives you the basic definition, simply the oscillation or vibration back and forth over the same path with the same time interval. A pendulum is an example of simple harmonic motion, or say the mass on the end of a spring could be simple harmonic motion. So I've got a couple pictures drawn here. This one we did in a lab to start the unit, where you took a mass and you pulled it down and then you let it bounce up and down like so, just to make sure we've got some of the terminology down. If it were, say, sitting here at rest, that is known as its equilibrium point, or where its position equals 0. Then if we say it was anything above here, we say that that change in position has got to be greater than 0, okay, or a positive amplitude. And then anything below it would be a negative displacement, or a negative amplitude. Now the other thing that we should make note of is that there are forces that would be acting on this, and they're always in the opposite direction as the displacement. Okay, if we have a negative displacement, the force is up. If we have a positive displacement, the force is down. I mean, this is the reason why it comes down. There must be a net force pushing down on it this way, okay, or pulling down on it in this case. Okay. Now, I'd also like to give you a different example here, where, say, we don't have to worry about gravity. We're just worried about the spring all by itself here causing the motion. If we put it on a horizontal surface like this, and we took the mass and we say we stretched it out this way and then let it go, okay, there would be a force that would pull it back this way, and then the spring would compress until it compressed enough so that it would supply a big enough force to push it back the other way, and then it would stretch, and then it would have a force this way, and it would compress and stretch this way. Okay, you can apply the same type of thing, the same type of rules. Here is where your equilibrium is. Okay, here you have a displacement that is greater than 0 as you stretch it. You can kind of think of this as like a timeline. If this is x, then everything over here is positive, everything over here is negative. Okay, so the same picture, they look the same, it's just that one is horizontal and one is vertical. One thing that I have to remind you of is that simple harmonic oscillators obey Hooke's law. If you don't remember what Hooke's law is F equals negative kx, because the force and the displacement are always in opposite directions. That's why the little negative's in there. Okay, so just something to keep in mind. All right, some basic terminology that you're going to need to know. Okay, displacement. Displacement, simply how far from the equilibrium point it is. You're going to usually see that written as an x, or delta x. Okay, amplitude, that would be the maximum displacement at any point, that could range from a to negative a. These are two terms that we've talked about before. The period is the time required to complete one cycle. So if I go back up to my picture, you know, it'd be if I stretched it out to here, it would be the time it would take for it to come back to here and then back out. Okay, that would be one period. The time required to complete one cycle gets the big capital letter T. And then the frequency would be the number of cycles per second. Okay, so it's actually the inverse of the period, and it gets the symbol F. Okay, so this is how frequency and period are related. Okay, frequency is the inverse of the period, or you could also think of period as being the inverse of the frequency. Okay, so in this case, again, just one thing to remind you of is that systems that obey Hooke's law, okay, are simple harmonic oscillators. Just something to keep in mind. Okay, now the next part here, I want to talk about the energy in an oscillator. Okay, so energy, oops, that shouldn't say is, that should say in simple harmonic oscillators. Now I'm going to talk about the horizontal component because it's a bit easier to talk about. Okay, if we think about the amount of energy that could be stored in that particular circumstance, it would either be the amount of stored elastic potential, because there is the spring being stretched, or you could think of it as the maximum kinetic energy. So sometimes we can think of the total energy in the system to be the combination of either how fast it's going or how far it's been stretched. Okay, you would get the maximum stretch when you were either at A, the maximum amplitude, or at negative A. Okay, so we can write a little expression here that says the total mechanical energy of a simple harmonic oscillator is proportional to the square of the amplitude. Because if I think about this, if x up here was actually a when it was completely stretched, well, when it's completely stretched, velocity will be 0. And I'm going to show you that in a couple minutes here. So if that's a, then that would be a squared. Okay, so oftentimes we will say that the mechanical energy is proportional to the square of amplitude, 1/2 k a squared. That would be when your system is at a and the velocity is 0. As long as v is 0, then that total energy would have to equal 1/2 kx squared. Okay, now if it was, say, at its equilibrium point, okay, not out at a, when a is equal to 0, then at equilibrium point, then all the energy is kinetic, and the total kinetic energy would be equivalent to 1/2 mv squared. Okay, so one thing to kind of talk about, let's put this all together. There's a connection between the period of a simple harmonic oscillator to an equation, and this is our equation. The period of a simple harmonic oscillator, a spring simple harmonic oscillator, is 2 pi square root of m over k. Okay. If we wanted to go ahead and write an equation for the frequency, we've got 1 over 2 pi square root of k over m. I just inverted everything because the frequency is the inverse of the period. Okay. Now, I'd also like to remind you, and we did this early in the year, we did a little pendulum lab, but a pendulum is also a simple harmonic oscillator, so in that case, the period is 2 pi square root of the length over the value of gravity, and if you wanted to find the frequency of that, it's 1 over 2 pi square root of g over L. Again, I just inverted everything. Okay. All right, so those are some basics to simple harmonic motion. We're going to get into a little more technical things here in the next video.